recording.
Okay, thank you.
Yup.
So as a yep. As a reminder, last week, oh my gosh, last week or yesterday, sorry, my bad. Nick over here covered all of this jazz. So talking about multiplying and dividing polynomials in a variety of ways. Um, Multiplying, we're talking about FOIL, we're talking about multiplying across. Dividing, we're talking about long division, we're talking about synthetic division. Um, Pretty heavy topics, to be quite honest. Rational root theorem, anytime you want to find the zeros. Um, and yeah, if there are any questions about that, please drop them in the chat or speak up. But we are going to move on to more factoring methods. So as Nick was saying, factoring comes up a lot in engineering. Um, so pretty much whenever you're given a polynomial, factoring it is going to be the number one way to find out any useful information about a polynomial. So here's just a quick little cheat sheet for you guys. Uh, these are just a few different methods of how to factor um, these polynomials that'll follow these sort of formats on the left here. So I kind of actually mentioned one of these, the difference of squares, the first one. It's anything like, x squared minus 9, anything where you have something to the second power minus a number to the second power. So generally speaking, A will be x, and then B will be the something that can be squared to be something, like 9 or 16 or 36 is a square, 25 is a square, anything like that. Sum of cubes, kind of same idea, except you get this sort of longer equation anytime you get a sum of cubes. Same thing, so A will generally be x, and then B will be a number, just like, any other number. Uh, you can also have the difference of cubes, which will have the pretty much the same equation, except you'll see that this sign is a negative instead of a positive, and this sign is a positive instead of a negative between the two equations. So they're kind of the same thing, but different. And then the perfect square trinomial is when we have a plus b, all of it is squared. So note that we have the squared on the outside there, which just means you break up a, trinomial into its two different parts, right? So nothing super groundbreaking there. Cool. Moving onwards, that hopefully, that might have been a review, a refresher.
And
We've
Rishi, what's the format for when you expand uh the addition of perfect squares? It's
addition
like
of
or like the last one, the perfect square trinomial. It's
mhm.
like a squared plus 2ab plus b
Mm,
squared. I think that's a good format to keep in mind as well if you see anything that looks like the
sure.
a squared plus 2 times ab plus b squared.
Yeah. Are you referring to a squared plus 2b plus b squared, I believe.
2ab.
2ab. Okay, there we
Yeah.
go. Yeah, that's a good way to write that out. Thank you. So, I mean, you could kind of take this fourth bullet point one step further and write it out like that. Yeah, a squared plus 2ab plus b squared. Perfect. Yeah, that's a good one to add on there. Cool. Next, we're going to talk about a quick little strategy. So sometimes you're given a problem or an equation, and it doesn't exactly look like anything super intuitive, right? You look at it and you're like, okay, well, x squared minus 4x equals 5. It's like, interesting. I don't really know what that doesn't follow any of the categories that I've seen so far. So what we do is we create a square. What we want is to make it so that the value, um, the c value, which in this case is kind of zero. I mean, there isn't a c value. It's like, a squared plus minus 4x plus c or plus 0 is equal to 5, right? There isn't a value there yet. You could subtract the 5 over, but there's something missing from this because 5 isn't really a square. And so in order to do this, what we need to do is create a perfect square by using this formula. So for problems for problems like this, so anytime you have like an x squared plus or minus some number times x, so in this case we have like 1x squared minus 4x equals 5. We can go ahead and use this formula, which will turn the entire left side into a square. And so we have a equals 1, b equals -4, and in this case, I believe c is 5. So that's the trick. I mean, it's just kind of a way to solve a polynomial in a way that's a little bit more familiar to us, or it'll become more familiar to us. So here we have that written out, nice and neat for us. We have our original polynomial. We add on that extra factor to both sides, which we got from this formula up here, the b over 2 squared. And our b value is 4, or -4, but that minus is just kind of subtracting our b value. And then we work out the math, so pretty much just go through and actually do the algebra, and we will get x minus 2 squared equals 9, or x minus 2 equals 3, or plus or minus 3. And then we can go ahead and solve. So if we have x minus 2 equals 3, we add 2 to both sides, we'll get x equals 5. If x minus 2 equals -3, we will get x equals -1. So that trick helps us a lot because if I'm being quite honest, if I look at this original polynomial, I don't really know how to solve for x in an easy fashion. I'm like, well, it could be anything, right? Like you can guess and check, but that's going to take a while. So this is a way to surefire every single time will definitely get you the answer. Anytime you have a problem that looks like this. Cool. And I will say, everyone, for some reason, my participant screen is kind of like phasing in, and I don't know if this ever happens to anyone else. It's going black and then it's coming back. So like for 1 second I can see Nick, and then 1 second I can't. Kind of weird, but I'm just gonna keep working through because it's not really an issue. But if anyone like raises their hand or something and I don't see it, my apologies. Cool. So moving on. Quadratic formula, guys. This is a super important formula because this also works every single time. This one, it's a little bit longer. You'll notice this formula it kind of sucks. It's kind of a longer thing. This is how to solve for x. How to solve for x in any polynomial. Well, I shouldn't say any. It only works for ones that follow this ABC format. So we'll have like ax squared plus bx plus c. So anything where the power is 2 for the first power of x. It's a good formula to know. You guys might have heard about it in high school, maybe not. But usually people kind of sing it. They're like, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Now, am I a singer? No, but that's what I sing in my head every single time someone wants me to recall the quadratic formula. I could even write it out right now without looking at the page. On God. Thank you, Nick. Much appreciated. I do see the clapping emoji. But it's true. I mean, mnemonics, is there going to be an equation in which you can solve with one way? Yes, good question. I don't know if it's Elena or Helena, but really good question. Yeah, so the quadratic formula is always going to be useful for what you could call it like the base case, which is when you have like an x squared. It's going to work every time, right? Because if you have, like, let's say we didn't have a bx and we didn't have a c, well, then we'd just say b equals 0, c equals 0. We'd still use the same exact formula. For example, if we were to say I don't know, y or f of x equals 1 x squared. If you wanted to solve for x um, in this kind of a formula, something like that, you would just say like a equals 1, b equals 0, and c equals 0. You'd use the formula and get your answer. There isn't something super um, specific that you need for the quadratic formula. However, for completing a square, you do kind of need a problem like this. So it says, for good reason, we use this for problems where we have like ax squared plus bx equals c. But this is usually going to be for cases where we don't already have a perfect square, right? If it was a perfect square, we would just, kind of use our intuition and find what those squares would be. Yeah, no problem. That was a good question. Good question. All right, and then last but not least, a little bit of vocab. Extraneous solutions in radical equations. So this is going to be uh, usually having to do with square roots. It's going to be a way to tell whether or not our answers are like the actual right answer. It's just kind of like a litmus test, or reality check, right? Anytime you're solving and you have square roots, it's good to kind of check that you actually have the right answer. For example, if we're given this problem, square root of x plus 5 equals 2, you do a little bit of subtraction, subtract 5 from both sides, you get the square root of x equals -3. So, one might think, maybe not you guys, but one might think that, if you square both sides, you'll get x equals 9, right? Because square root of x squared is x and -3 squared is 9. However, that's not true. Yes, each of those statements taken on their own could be considered true, but if you actually check that answer, right, if you plug back in x equals 9 into this, we're going to get the square root of 9 plus 5 equals 2, which means 3 plus 5 equals 2, which means 8 equals 2. And I don't know about you guys, but I think that's a little bit suspicious because last I checked, 8 is not equal to. So extraneous solutions are solutions that are not included in the actual solution set. So they're just not true. Yeah. So for this guy, I believe Nick, you correct me if I'm wrong. I think the answer, um, well, if I was to get this on a test, I believe it'd just be false. No? What do you think? What do
I
you think?
I don't think there is a solution to this,
Yeah, it'd be
even
false.
with
I mean,
like complex numbers.
yeah,
Still no.
because I mean, I'm thinking through with eyes and whatnot. Yeah. So the answer would be no solution is how I'd write that. So if you plug this into your calculator, it would say false. Um, no solution. We'd box that guy um, because it's an extraneous solution, right? The answer would be 9, but that's not true. It doesn't work. So I'll tell you guys right now, generally you're going to want to do that anytime you're dealing with square roots or squared. Just go ahead and check and make sure, plug back in your solutions at the end, and make sure you're not adding any solutions. What happened here is technically by squaring both sides of this, you're actually like adding an extra solution, which wasn't originally there. And so be careful. Never divide or multiply and add some extra solutions if you're not sure. Cool. Well, any questions so far? They're making good pace. Good time. Good time. Cool. Yeah, I mean, these are kind of just like tools to have in your toolkit. Um, the more you look at practice problems, the more you will use these kinds of strategies. So let's use them, right? Let's jump into it. We're gonna do problem 1 here, factor these rational expressions, and note their format, right? So they're pretty much saying you don't need to just spam the quadratic formula every single time, right? Like, you should generally use whatever strategy is most appropriate, and try to use a variety of strategies if possible. So this first one here, anyone have any ideas which strategies we could use for the first problem? I'm looking at this guy on the left. Feel free to shout out, either the answer or the strategy from earlier. As a reminder, the strategies are up here. Okay, okay. So I'm hearing a perfect square is a perfect square, which is true. Um, so yeah, this one right here pretty much becomes x plus 5 squared, right? Because this number, this b value, or sorry, that's not a b value. The anyway, it's that number there, which you could say it's half of the b value in this case. Essentially, if you add this number to itself, so 5 plus 5 equals b, which is 10, and then 5 times 5 equals c, which is 25. So that number there works perfect for a perfect square. Next, we are going to talk about this problem here. Any ideas? What does that look like to you? X cubed plus 125. All right, I'm seeing in the chat we have sum of cubes. Yeah, that's right. So here, what we're going to go ahead and do is break this guy up into, or not break it up, but simplify it into x to the third power plus 5 to the third power. Because 125 is 25 times 5, and 25 is 5 times 5. So using that formula from above, it's going to be x plus that number 5 times x squared minus that number, which is 5, times x plus 25, which is 5 squared. I have it pulled up on my computer, but it's always handy to have those tools whenever you're looking at problems like this. Cool. We're going to go ahead and box that guy. Oh, not a good box. We're going to go ahead and box that guy. And we can box this guy over here as well. Moving on to problem number 3. I'll tell you guys right now, it's a little bit of a funky problem because we've got y's there, but this is still a perfect cube. So what I'm going to do is actually pull out a 2 to make things a little simpler and multiply that 2 by x cubed plus 64y to the third. So once I pull out a 2, we have a perfect cube. The reason I know it's a perfect cube is because I play the game 2048 a lot. And so I know that 64 is, I think, 2 to the 6th and 2, which is equivalent to 4 to the third. Because 4 to the third is equal to 2 squared to the third. I'm doing a lot of extra math here, guys. I'm just trying to tell you guys that's how I know that is a perfect cube. But in any case, we're just going to go ahead and pull that 2 out, keep it there, and then we're going to do x plus whatever that number is, whatever that cube root is, which is 4, times x squared minus that number, 4 times x, plus that number squared, which is 16. All right, all right. And then last but not least, another tricky one. We have 4x all squared minus 48x plus 6 squared. So I'm just going to kind of rewrite this 48 a little bit because 48 isn't a super intuitive number to me. I'm going to write that as 2 times 4 times -6. The reason I'm going to do that is because I'm going to write this 6 squared as -6 squared, and then this 4x as 4x. I don't touch that. So pretty much what I'm doing is I'm trying to rewrite everything in terms of the same kind of numbers. Um, I'm seeing like what are the factors of 48, right? So we covered that yesterday, I believe, talking about how we can break up um, numbers into their smallest components, right? So we can break up that 48 into uh, 24 times 2, and that 24 we can break up into the factors that appear in other parts of the problem, right? So since there's a 4 that appears here and kind of a 6 that appears over here, that's how I know to break it up into 4 and -6. This one is a little bit more complicated though, so don't stress it if that doesn't like, you know, that wasn't like your first intuition, because it wasn't mine either. I mean, this is a pretty weird kind of a problem. But if you look, this is actually a perfect square. It's a perfect square with a 4 attached to the x. So we have a coefficient of x, 4x -6, all squared. So I'll get us 4x squared. Let's see, minus 2 times 6 times 4 plus 36, which is what we started with. Does everyone kind of see how that last problem is a perfect square? Give me like a thumbs up if you're feeling good. Shouldn't there be a y in the solution? Good question. Let's see. So we have two. Hold on, let me pull up my handy dandy little cheat sheet again for the sum of cubes. We'll have a plus b.
Oh, yeah, I think I might have made a mistake in writing this solution, but it should be x plus 4y and then x squared minus 4xy plus 16y squared.
Okay, so we just kind of left out the y.
Yeah,
Gotcha.
that's my bad.
No, you're good. No worries. That I mean, glad people are paying attention. Am I right? I mean, that's the real goal here. So let's see. There should be a y over here, no?
Yep,
And then a y over here,
y squared.
y squared. Okay, perfect.
Good catch.
Yeah, yeah, really good catch. There we go. Yeah, see, people are paying attention. That means they're ready for the MPE is what that means. Okay, they're locked in. We're not locked in. They're locked in. All right. Um, cool. Well, if there's no other questions or mistakes with that first problem, let's move on. Cool. Problem 2. So, I mean, there's a good number of parts to this. For the sake of time, let's have you guys' feedback. Let's have hmm, okay. Since I think we all get our emojis in the same order. So if you want me to do like one problem, give me the clapping hands emoji. If you want me to do two problems, two of these three, give me the thumbs up. Give me the crying laughing emoji if you want me to do all three problems. For the sake of time, I don't want to go through all three. If you guys would prefer to see more material from somewhere else and you know, do the rest on your own time. Cool. Okay. Cool, cool, cool. So for those of you who do want to see two or three, I'll let you guys know. Nick, the solutions are already posted for this or will be shortly. Already posted. Okay. Solutions for this are already posted, guys. So if you really wanted, you could look at them right now. They're in the Discord worksheets channel. So don't sweat it, guys. Nick's wonderful mistake-free solutions will be on the Discord. We're gonna do problem 1 to make things simple. Problem 1 here. We're gonna factor the rational expressions by completing the square and by doing the quadratic formula. So completing a square, we're gonna look to create a square somewhere in here. X squared plus 2x. What I'm essentially going to do is divide that b value. So here we have b equals 2. We're going to divide that by 1, and we're going to square it, right? So I believe the kind of handy-dandy little formula was b over 2 all squared. But let me fact check that, because I don't want to lead you guys astray. Yeah, there it is. b over 2 squared. So we're just going to find our b over 2 squared value. So here we have 2 over 2 squared, which is 1 over 1 squared, which is 1. So all I'm going to do is I'm going to add 1 to the left-hand side. I'm also going to add 1 to the right-hand side. That's going to create a perfect square, because now our left-hand side, by virtue of that addition, becomes x plus 1 squared. Right-hand side will become 8, just because we just add the 7 to the 1 that we just added. Whatever you do on the left hand side, you must do on the right hand side, of course. Next, I'm going to square root this guy. So x plus 1 equals plus or minus the square root of 8, since we square rooted both sides. So now we're going to have two possible solutions. We're going to have x equals -1 plus or minus rad 8. So we're going to have x equals -1 minus rad 8, or -1 plus rad 8. Cool. Next, we're going to use the quadratic formula for the exact same problem. So I told you guys I could do it from memory, okay? Hopefully you guys can too. I don't know if I'm special or not, but x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And just as a reminder, we have an a equals 1, a b equals 2, and our c in this case will equal -7. Sorry, I'm getting kind of cramped here, so I'm just going to go ahead and, or I'll move that to the side just in case anyone's still writing it down. Oh my gosh. There we go. It's kind of awkward there, but that's okay. C equals -7. Anytime you're completing a square, you're going to want to rewrite your formula with a 0 on the right-hand side. So I essentially rewrote that as x squared plus 2x minus 7 equals 0. And then it becomes really clear what our a, b, and c values are. Once we have that, we can plug them in here into our quadratic formula. You can have x equals -2 plus or minus the square root of 2 squared minus 4 times 1 times -7 all over 2 times 1. We just carry through with our algebra. We should get x equals -2 over 2 plus or minus, let's see, the square root of 4 plus 28 all over 2. X equals -1 plus or minus the square root of 32 all over 2, which is equal to x equals -1 plus or minus. And then we're just going to go ahead and break up that square root as much as possible, which is going to look like a 4 times 8 over 2. The reason I chose 4 times 8 is because 4 has a square root. And so I can break this up into our final answer of -1 plus or minus, or I'll show it real quick. 2 rad 8 over 2, which is equal to -1 plus or minus rad 8. Cool. So I know I wrote out the steps a lot, but guys, I'll tell you right now, on a test, what are the chances you're going to mess up something like this? Could be kind of could be kind of low, could be kind of high. I don't know. That depends on everyone. But for me personally, the chances that I'll make a mistake somewhere in this problem is pretty high. And so writing out your steps like this is always going to be good practice because eventually in most of your classes you're going to start getting a lot of extra credit or partial credit. Sorry, maybe you'll get some extra credit. I don't know, but you will get partial credit for your work and your solution. I actually took a class just last quarter, fluid dynamics, and the correct answer was worth about 2 to 4 points, and the work for the entire problem in total was worth about 35 points. And that's not an exaggeration. Like um, you could get the right answer and do everything else wrong. You'd only get 2 points. But if you showed your work, I mean, it didn't even matter. It didn't even matter if you got the right answer. They just care if you know how to do the problem. So if I write this out, let's say I made a mistake and I couldn't factor this out right and I accidentally factored out a 4 and then I ended up with like an extra 2 over here or something like that, I would still get like 90% of the points. 90%. So just trying to instill that habit in you guys is all. Cool, cool, cool. Looks good. So real quick, I'm just going to go through PolyQ 2.3, and then I think we'll be able to hand it off to Nick. Um, and then Nick, are we thinking breakout room somewhere in your section? You want to do it in between? What are your thoughts? Or do we want to do no breakout room for today?
I mean, I don't know if we need to do a breakout room. We
Okay.
can if you want, but I mean, my problems don't really facilitate it.
Okay,
Um,
cool.
I have a,
We
f-
can we can always do the
I have a feeling we'll probably end early.
Okay,
And
cool. I like it. Yeah, yeah, yeah. No, we can always do a little bit of, a day in the life as we discussed. Day
sure.
in the life. But yeah, okay, I was just gonna check before this problem. So, without further ado, real quick, rapid fire. So we have square root of x equals 7. We can go ahead and say that x must equal 49 because the square root of 49 is 7. Uh, that's kind of like our base case, right? We don't have to do anything crazy. For part B, however, we have the square root of x equals -7. Oh, did not mean to undo that. This is kind of like what we saw earlier. Uh, we have an extraneous solution. So we have no solution for this problem, right? Because if we were to multiply both sides or square both sides rather, we would get x equals 49. However, the square root of 49 does not equal -7. So therefore, x does not equal 49. For C, we have the cubed root of x equals 7. So that means x equals 7 to the third power. Oh, 7 to the third power, which is equal to 49 times 7, which is equal to 343. Part D, the cubed root of x equals -7. Um, what do we think here, guys? What do we think here? Any uh any audience feedback? Okay, no solution, no solution. Well, I'll tell you guys, this is a trick question. It's not actually a trick question, but it's a learning opportunity. Since this is an odd power, since this is an odd power, x equals negative 343. Um, and so you can actually have an odd power that gives you a negative. So if we were to plug back in um, x into this cubed root, x equals, or cubed root of x equals that, we would get -7, right? Because if we have -7 times -7 times -7, that's the same as 49 times -7, which is in fact negative 343. And so the odd power actually makes it so that there is a solution. So a little bit of a tricky one there. Okay, last but not least, part E. I'm going to ask you guys again, what do you think? What is the answer? There we go. I'm seeing no solution. And that's right. So this one's kind of just a reality check, as I mentioned earlier. Um, you have something, you subtract one from it, it cannot be equal to whatever you subtracted one from. I mean, essentially, if you subtract rad x from both sides, you'll get -1 equals 0, which is not true. So there's no solution. No sol. Cool. Cool, cool, cool. Well, that's all I got for module 2. A little bit of solving polynomials, a little bit of checking extraneous solutions. Good fun, good fun. Nick, I'm going to pass it on to you. Um, and you can, yeah, take it away. Take it away.
Thank you very much, kind sir. Okay. Give me a sec. Okay. Here we go. Here we are. Okay. Cool. So, getting into the next section, we are going to talk a little bit about graphing polynomials. And before we do that, a small little detour to talk about functions just in general and some terminology surrounding them. So we define functions in math as anything where you plug in some input, usually x, and you get out some output, which a lot of the times we read as f of x or g of x or any letter of x. And a lot of the times we plot that on the y-axis, right? So we get x, y coordinate pairs. Now f of x, broadly speaking, refers to anything where we plug in an x and get something out. So x squared is an example. Any polynomial, all the way up x to the fourth, x to the fifth, all work. F to the x equals sine of x works equals e to the x. Any of those are things we can denote as a function. And plugging in a number to a function, such as here f of 5, is just replacing x with 5, right? And solving for that. Now, with multiple functions, in this case, we have an f and a g. We can sort of treat these f of x and g of x as a stand-in for these guys, the x squared and the 3x. What I mean by that is writing something like g of x plus f of x is the same thing as writing x squared plus 3x, right? If g of x was sine of x, same thing. We're just adding the functions together. Same thing with multiplying. Here g times f. it would be the same thing as 3x times x squared. So multiplying those functions gives us 3x cubed. And then finally, the last one is an operation that's specific to functions, which usually we say is called composing. And it happens when you plug in a function as an input to another function. In this case, this is written as f of g of x. And what that means is, in this case, this is the input to f, or in other words, x, right? So f here is x squared, and so f of g of x is 3x squared. We're just plugging in 3x where the x was in f. A lot of the times this will be written, and I really hope this is the right order, but this will be written like this, where this little circle denotes f of g of x. So if you ever see that circle like so, I know here it looks like the word fog, but really that's just supposed to be a little open circle, which means composed. Okay, so just a little detour, a little review there with some terminology on functions. Before we move on to what the polynomial graphs look like. So any polynomial can be written in this form, right? Where we have these coefficients a sub n minus 1, all the way to a sub 0. And then we have x to the n, x to the n minus 1, all the way down to x to the 0, right? Which is just 1. And the degree of a polynomial is whatever n is, the largest exponent. It turns out the degree of a polynomial is the most telling thing about what a polynomial's graph is going to look like. Because, and this is maybe getting a little calculus-y, but that's going to be the term that grows the fastest as you plug in larger and larger values of x. For example, x cubed versus x squared, right? Plug in 10 to those. This is 1,000. This is only 100. So the larger term is going to impact what the size of the function is way more than the smaller term. So it's for this reason that the leading term usually determines what a graph looks like more than any of the other terms do. Okay. So we'll look at this leading term, and there's a couple sort of buckets we can put these functions into based on what the leading term is. So first of all, even powers, such as x squared, such as x to the fourth, x to the sixth, stuff like that, is always going to have this kind of U shape. Now, whether it opens upwards or downwards depends on the sign of the leading term. So if the leading term is positive, a sub n is positive, then it's going to open upwards, right? It's going to grow up like that. If a sub n is negative, that first term is negative, we can imagine the graph just gets flipped upside down, right? It's the same thing as taking all your inputs and just reflecting them about the x-axis, or all your outputs reflecting them about the x-axis. Yeah. And then, okay, if all of the even powers look like that, then what is their differentiating x squared and x to the fourth and x to the sixth? Because surely they must look different. And they do. X squared, this is what x squared looks like. As we move up in powers, you can imagine when we plug in a small number and raise it to a really high power, it's going to get smaller and smaller and smaller really fast. You know, multiplying 0.1 by 0.1 by 0.1 by 0.1 is going to approach 0. And so the first difference you see, for example, if it's x to the fourth, is the area really close to 0 is going to be way flatter than x squared or a lower power because all those low values are being squished down to 0. Now, somewhere here, we're going to get to 1. And right, this is always going to be on the graph no matter what. 1, 1 is always going to be on the graph. But beyond that, now, because the power is so much higher, now we just shoot off at a much faster rate than x squared or just a lower power, right? So the main difference you're going to see as the power increases is the lower part is going to squish down and these parts are going to shoot off much faster. Hopefully that makes some sense, considering the power is bigger. And then obviously same thing, but just flipped for a negative sign. Okay. If the power is odd and the sign is positive, then we're going to get something that looks like this. For example, this is x cubed. We can sort of see earlier why we have solutions for negative values with odd powers. It's because we actually dip into the negatives with odd powers. Because you can actually achieve negative numbers with odd powers, right? So here we go from negative infinity, do a little S shape around 0, and then go off towards positive infinity. Having a negative sign in front of it is just going to flip it, just like we saw before. And then as we increase the coefficient, or not coefficient, the exponent to 5 to 7 to just larger values, you're going to see once again, this is going to be super steep and then be super squished and then be super steep, which I guess I didn't do a very good job of drawing it differently from the other one. But you see like this area very squished and this very steep as x to the 5th, x to the 7th, so on. So that is going to be the main difference as we increase the power in these graphs. And obviously this is just a pure x cubed, right? Adding other terms like an x squared term, a x term, a constant term are going to affect how these graphs look. But overall, the end behavior, so what happens as x goes to infinity, what happens to the ends as they shoot off, is going to be determined by that leading term. So even if this area is, you know, weird or whatever, as long as that leading term is odd, then we're still going to have this sort of end behavior here. Okay, cool. All right. Any questions on that? Does that make sense? Thumbs up. I guess there's no thumbs down. Okay, cool. All right. So last thing before we do a couple examples. This is interesting. This feels a little misplaced. Rational roots. But last thing we'll talk about is the equation of a circle. So graphing a circle is kind of weird. It is a dual input equation basically, where x and y, it seems, are both inputs. Now, you could plug in an x and solve for the corresponding y, but this standard form has x and y on the same side, which is maybe a little different from what we're used to seeing. But typically the format of a circle equation is you have x minus h squared, where h is the x coordinate of the center of a circle. So if this is our graph and we have a circle over here, then this is h and this is k. So we have x minus h squared plus y minus k squared, where this dimension here is r. R is the radius. Um, yeah. And then sometimes we will expand that into this general form. I don't I don't know what that is really all about. You're never ever gonna write a circle equation in that form. You might get given it in that form and try and put it in this general like standard form, but if you're graphing or working with circles, it's always gonna be in this first form right here. Okay. Um, Although interesting to note, if you did have it in this form, you would probably have to do some kind of completing the square to get it to the other form, which maybe makes sense based on the format. Okay, cool. Any questions on any of the material we talked about before we do some examples? All right, cool. All right, we got two examples to do. The first one, I'll be honest, I don't know why it's in this section. It seems like it should have been in the previous one, but this is the order it was given in uh the practice modules, so we'll run with it. Uh, find all possible rational roots of the polynomials. In this case, we're going to use the aptly named rational root theorem. I'm going to do two of these examples and probably leave the third one up to you guys if you want to try it. Um, but yeah, let's see what we got. So I'll do this first one here. And recall what the rational root theorem is saying is that all the possible rational roots are all the possible here, all possible plus minus combos of factors. Oops, got the big eraser. Of factors of a naught over factors of a sub n. So first thing we got to do is we got to find those factors. This guy's a0. This guy's an, in this case a sub 3 probably. So for problem 1, shall separate off like this. A0 equals minus 6. An equals 6. So let's break this into its factors, which are going to be 1, 2, 3, and 6. And we got to remember that each of these can be plus or minus, according to this theorem. We got the same number here. So once again, 1, 2, 3, and 6. And these guys can be plus or minus as well. Okay. So all possible rational roots are going to be the plus minus factors of a naught over factors of a sub n. So plus minus 1, 2, 3, 6 over 1, 2, 3, 6. Now, what are all these combos going to be? Well, each one of these numbers can be either positive or negative. And we're just going to look at it like this. If we divided 1 by 1, we get 1. If we divided 1 by 2, we get 1/2. 1 by 3, 1/3. And then 1/6 for 1/6. Then we move on to 2/1. It's going to give us 2. 2/2 is just equal to 1, which we already have. 2/3 gives us 2/3. And then 2/6 simplifies to 1/3, which we already have. 3/1 gives us 3. 3/2 gives us 3/2. 3/3 gives us 1, which we already have. 3/6 gives us 1/2, which we already have. And then finally, we have 6/1 gives us 6. 6/2 gives us 3. 6/3 gives us 2. 6/6 gives us 1. And so this bank here is all possible rational roots for this expression. We have, as you can see, 9 distinct numbers. Each one could be positive or negative. So we have 18 possible rational roots to this expression. Now, according to the theorem, the place you would go from here, you would say, okay, well, now let me try each one of these and see which one divides evenly into this polynomial. Now, that sounds like a lot of work, and that is, not ideal, but I guess that's, in theory, that's what this theorem allows us to do, right? These are the only ones we'll ever have to test, assuming all our roots are rational. Okay, cool. Hopefully that made sense to you guys. I'll blitz through one more example. We'll do the second one now. So 2, where a sub 0 is 9, and a sub n is 4. 9 factors into 1, 3, and 9. 4 factors into 1, 2, and 4. And these are all plus minus. So all possible rational roots are plus or minus 1, 3, and 9 over 1, 2, and 4, which are, we'll go ahead and find all those combos in the same pattern. So I'm going to start with 1/1 gives us 1. 1/2 gives us 1/2. 1/4 gives us 1/4. Then 3/1 gives us 3. 3/2 gives us 3/2. 3/4 gives us 3/4. Then 9/1 gives us 9. 9/2 gives us 9/2. And 9/4 gives us 9/4. And so once again, we have 9 distinct numbers and 18 distinct roots that we can check here, using synthetic division or long division, whichever one you can prefer. Yeah, it doesn't look very, very nice. But here's the thing. If you were to just guess what the factors were, you may never guess it. If you do this, you at least are guaranteed to, in some reasonable amount of time, guess at least one of the factors. And in theory, once you get one of the factors, then the rest is easy from there. But yeah, okay. So I meant to go over some examples of the rational root theorem last section. This is what it's talking about. when we do that. And maybe you'll find a use case for it. I hope you can find a use case for it. Okay, cool. All right. Last thing we'll talk about, we'll see if just by observation we can put our knowledge from today to the test and predict how functions will behave based on that leading term, like we talked about. So in each case, we want to identify what the degree of the function is, the sign of the leading coefficient, and then most importantly, what it does all the way to the left on the graph and what it does all the way to the right on the graph. So degree should be pretty easy. We can just look at that. We have, first off, a degree 2 polynomial, right? This next one, also degree 2. Degree 3, I'm just looking at the exponent. Degree 5, and degree 4. Okay. Here, we want to identify whether the leading coefficient is positive or negative. First one is going to be positive. This is going to be negative. Here we have positive 2 as our coefficient, so that's a positive. Negative 4 as our coefficient is negative. And then positive 2, that's a positive coefficient. Okay. Now using our knowledge of each case, let's go through one by one and try and identify what it's going to look like. So I want you guys to put in the chat for each one. We'll have, I mean, either side will either increase or decrease, right? So for the first function, what will the two behaviors look like on the left side and the right side as we go to infinity? Yeah, both will go to positive infinity, right? And I'll just write increasing, right? And that makes sense. I mean, we've seen that function before, x squared. It's just both going to positive infinity. Next, we have a degree 2 polynomial with a negative leading coefficient. So what can we expect? Decrease. Love to see it. That's the equation describing my crypto wallet portfolio in 2021, right after it all started going down. All right. We got degree 3 with a positive leading coefficient. What can we expect from both sides? I'm not even gonna try and do this with my hands. It's just gonna come out terribly. Yeah. Yeah, negative infinity and positive infinity. The right side of that equation, that's what everyone else's crypto portfolios did right after I got rid of all of mine. Just all to the moon. You always miss. Okay. Fourth one. Fifth degree polynomial. We may not know exactly what this is going to look like. Probably haven't seen a ton of fifth degree polynomials in our time, but it's fifth degree with a negative coefficient. So what can we expect? Yeah, good stuff. Positive, negative, right? Backwards S shape. Okay. And finally, we have a degree 4 polynomial with a positive leading coefficient. Yep. Perfect. Both going positive infinity. And that's what everyone here's math knowledge is doing as you're attending these sentences, these sequences, approaching positive infinity. Yay. Okay, perfect. It seems like we got a good handle on that. And with that, uh, we have problem set questions that I highly encourage you guys to try. Specifically, these guys are sort of on some of the newer material. The first couple are just some warm-ups on sort of dealing with rational expressions. But yeah, that is the end of the polynomial section, and we are now halfway done with all the content we'll cover in this course. So clap it up, clap it up. Um, Good job, everyone, for making it this far. Um, Love to see it, love to see it. At this point, we are done for the day. Um, I mean, I was planning on, I know you guys are all incoming freshmen at UCSD. Um, I'm sure you guys have all sorts of questions on UCSD, either, student life or not student life, classes, clubs, organizations, anything like that. Rishi and I have now been through the ringer. We've seen lots of, but not all of what UCSD has to offer. And I want to open the floor to you guys. If you have any kind of questions about our experience as UCSD engineering students and just people that lived on campus, uh, open the floor to you guys. Obviously, you're not obligated to stay or anything. We finished all the math for the day, but in case anyone's curious, we're here opening the floor for questions. And office hours will still be at 4 after this section is over. I believe I'm hosting them today. Right, Rishi?
Yeah, I mean, or whenever the section's over, they'll be in the Discord, Discord office hours. Yeah, one or both of us will be there.
Cool.